Okay, hello everybody. Today we're going to have Daniel Mata. Uh, he was a PhD student, but from very recently now he's a postdoc student in Abu Dhabi. But now he's at the Centro de Investigación y Estudios Avanzados del Instituto Politécnico, Nacional, sorry, in Mexico. And he's going to speak about Lorentzian vacuum transitions in canonical quantum gravity. So go ahead, Daniel.
Thank you. Well, let me start by thanking the organizers for this opportunity. So let's start with this seminar. So first of all, I want to talk about what we mean when we say Lorentzian vacuum transitions. And we're going to talk a little bit about the framework of canonical quantum gravity, and then we start with our results. So the general setup is this. We're going to have a scalar field, which is canonically coupled to a theory of gravity. This scalar field has a scalar field potential with this general scenario where we have two minima. One minimum has a greater energy, so it's a false minimum, and one minimum is the true global minimum, so it's a true minimum. And by quantum tunneling, we can have transitions from the false minimum to the true one. And we're going to compute the transition probabilities for these to occur in the framework of canonical quantum gravity. This is the general set. So these transitions were originally studied by Sidney Coleman and Frank Lucia in the 1980s. They used an approach to quantum gravity employing a Euclidean path integral. And this process is described by nucleation of two vacuum bubbles. It is similar like when you have water and you heat it up, bubbles start to nucleate. So it is similar. What is being nucleated here are entire spacetimes. And one important result is that when you consider transitions not between two different minima of an scalar field potential, but between two different values of the cosmological constant, the end result is a closed universe. Now, it was all with Euclidean methods. But now using Lorentzian methods in the early 2000s, it was developed by Filser, Morgan, and Polchinski, employing the Wheeler-DeWitt equation. And this method was improved in 2020 by Fernando Quevedo and collaborators, where they studied as well transitions between two values of the cosmological constant, and they found that the end result can be an open universe, so it is in contradiction with the Euclidean method. So they thought that it was important to study more about this topic with the Lorentzian method. Now, they studied also the transitions between two minima of the scalar field potential in a very particular setup in 2020, and they obtained results that coincide with the Euclidean methods. In the simplest model, which is a Friedman, Limit, Robertson-Walker metric in general relativity. Now, with the Lorentzian methods, there is, in this formalism, there is not a description of overnucleation. We can only have a comparison between two static solutions, but what we describe is transitions describing the creation of universes by this vacuum decay. This is a generalization of the standard paradigm of canonical quantum gravity, which is the tunneling from nothing scenario. In this case, we are not having a tunneling from nothing, it's a tunneling by vacuum decay of the scalar field minimum. Now, our contributions are, first of all, we propose a general method to compute this transition probability, which is applicable in principle for any model in the mini superspace. I'm going to talk about what those mini superspace means in a moment. We use this method in different theories of gravitations and in various scenarios. And very recently, we also have computed quantum gravity corrections to the transition probability, going beyond the first semi-classical results. So let me talk about a little bit what is the paradigm of canonical
Daniel,
quantum gravity.
I have a question, if you don't mind.
Yeah.
First of all, I'd like to say that I'm very interested in your seminar and your work, because I also work on canonical quantum gravity, but more on bouncing scenarios. Anyway,
okay.
So a typical problem that I always ask people is when you are computing probabilities in the mini superspace, how do you interpret these probabilities?
Okay, I'm going to talk about it in a minute.
Okay. So I can return to this.
So yes, let's talk about a little bit canonical quantum gravity first. And then we are going to talk about the general method and how we interpret these probabilities. So the canonical quantum gravity approach employs the Hamiltonian construction of, in particular, general relativity. That is, we employ the ADM formulation. We foliate the space-time by a hypersurface of constant time. And we have the last function and the shift function that tells us how to move between those hypersurfaces. And in the canonical formulation, those functions are Lagrange multipliers. The degrees of freedom, the real degrees of freedom, are the trimetric and the matter content that the theory could have. So in this formalism, we are led classically to the Hamiltonian and momentum constraints. For homogeneous metrics that only have a few degrees of freedom from the metric, all the information is encoded in the Hamiltonian constraint. So we employ canonical quantization of constraint systems, the method proposed by Dirac. And in this quantization, the coordinated space is called superspace, which is the space defined by the degrees of freedom of the trimetric and the matter component. It has nothing to do with supersymmetry. It's just called superspace. So as I said, for cosmological applications, when we have homogeneous metrics, we say that we employ a mini superspace approximation because we only have a few degrees of freedom coming from the metric. Now, all the information is encoded in the Hamiltonian constraint that turns to the Wheeler-DeWitt equation, which is the Hamiltonian, the total Hamiltonian of the system as an operator, annihilates a wave functional, which is called a wave functional of the universe. Now, the interpretation of this wave functional is an ongoing debate. It has a lot of proposals to try to understand how to interpret these solutions of the Wheeler-DeWitt equation. And what we are going to employ is a proposal which states that the ratio of two solutions of the Wheeler-DeWitt equation is a transition probability between both configurations. It's a conditional probability, but when we define those solutions in a very specific form, we can have the transition probability between both configurations. So that's what we are going to employ the interpretation of these solutions as conditional probabilities. In a moment, I'm going to talk about specifically how are going to be those two solutions. Oh, okay. So now let's talk about the general method. We are not going to restrict to a specific theory of gravitation. I mean, we're not going to restrict ourselves to general relativity. We are going to try to stay as general as possible. So we're going to start our method by considering a general Hamiltonian constraint. The fields of mini superspace are going to be denoted by phi m. The canonical conjugate momenta are pi m. So we're going to have kinetic term, which are quadratic terms in the momenta with mini superspace metric. Then we're going to consider a vector in this mini superspace, which is constructed by linear terms in the momenta, and then a function f that does not depend on the momenta. Here is where is going to appear the potential of the scalar field and every other term that can appear that does not depend on the moment. So the Hamiltonian constraint is in this form, and it is 0. So the Wheeler-DeWitt equation up to ambiguities in the ordering takes this form. And we're going to employ a WKB type ansatz, where this S function has a semi-classical expansion. S0 is the classical action, and all the other terms are going to be quantum correction terms. So the semi-classical result will be when we only consider the classical actions, and the first quantum correction will be considering the S1 and so on. So when we substitute these answers into the Wheeler-DeWitt equation, we obtain an independent equation for every order in H bar. For the first two powers in H bar, we obtain this. In the first equation, we only have S0. The second equation, we have S0 and S1. The third equation will have S0, S1, S2, and so on. Now we define integral curves on the mini superspace. We're going to use an auxiliary parameter S and an auxiliary function C of S, defined in this way. And in this way, the Wheeler-DeWitt equation turns out into this expression. And the S0 function, the classical action, can be written as an integral on the special slice of the being considered, and an integral of the S parameters of functions that we are already know. So if in particular, equation 10 and equation 11 form a system of equation for these variables, the derivatives of the fields on mini superspace with respect to this parameter, and the function c squared. And this system of equation has the same number of variables as the number of equations. So in principle, it can be solved for any model in the superspace. And when we can compute it, we can return here, and we can compute S0, and then have the solution of the Wheeler-DeWitt equation up to only the first term in the semi-classical expansion. In the case where we have only dependence on the time variable, that is the homogeneous case, the equation takes the form of a differential equation, an ordinary differential equation, where here appears a term volume of X, which is the volume of the special section. When we consider metrics that have a compact special slice, this will be a number. When we have metrics that do not have a compact special slice, we will have to compactify, or we will only call it an overall constant, which is volume of X. Now, in the generic form in which we do not have linear terms in the momenta, where the Hamiltonian constraint only have the kinetic term and the F function, the system of equation has a general solution, which is this. And in particular, the solution for the different fields in the superspace is to this expression. So the different fields in superspace will not be independent, they will be related in such a way that the transition probabilities will always have a dependence on 1 degree of freedom coming from the metric. Okay, now this is the way in which we obtain a solution of the Wheeler-DeWitt equation. We now move to the transition probabilities. So as I have already said, we are going to consider the interpretation of conditional probability. So we have two solutions, and the ratio of those solutions are going to be interpreted as a conditional probability. So in the first solution, we're going to have all the degrees of freedom coming from the metric are going to start at 1 point and are going to evolve until a final point. Everything is parameterized by the parameter S. In one solution, the scalar field will change from the true minimum to the false one, and the other solution, the scalar field will remain to its false minimum. So in this way, this ratio can be interpreted as the transition probability of having this vacuum decay between the false minimum to the true one. So consider only the first term, the semi-classical result. We have the transition probabilities written in this form, where this gamma will be this difference of this classical actions evaluated in the two different paths, and we will have a sign ambiguity because the general solution will be a linear superposition of exponential terms, but we will only consider the biggest contribution. So that's this is going to be a sign ambiguity that we're going to choose in such a way that the probability is well defined. Now, in order to consider quantum corrections,
yeah. I have a question.
Okay.
In the last slide, you told about conditional probabilities between scalar field configurations, but since the wave function depends on the metric, so you are considering conditional probabilities between a configuration of the scalar field and the metric, or are you considering that just the scalar field is changing its configuration? I didn't get this point.
The metric will be the same. The only thing that changes between these two solutions are the scalar field. So we're going to be a conditional probability between two configurations of the scalar field.
I got the idea, but why can you do that? Doesn't the wave function depend also on the metric?
Yeah, it depends on the metric, but it will be the same metric in both sides.
Okay, fair enough. Thank you.
Okay. You're welcome. So yeah, this is going to be the semi-classical result. In order to have quantum corrections terms, we need to consider higher orders in the WQB expansion. In the simplest and as I said, will be generic case in which we do not have linear terms in the momenta. The quantum correction to the transition probabilities will have this expression. We're going to have the same expression with gamma, but now gamma will have three contributions. We only are going to consider up to second order quantum corrections because there is where things are going to start being interesting. So the first term is the same as before. The second term is going to be the first quantum correction. It has the same expression as before, but now instead of S0, it's S1, and the second quantum correction is going to be S2. And the overall dependence in H bar changes because they appear in the semi-classical expansion. Okay, so this is the general method. And S1 and S2 are also going to be computed as integrals on the S parameter. So once we solve the system of equation, we can in principle solve for S0, for S1, and for S2, and have the transition probabilities of to any desired order that we want. So this method is general. It only depends on a generic form of the Hamiltonian constraint. So we're going to be able to apply it to different scenarios. So it is applicable in principle to any model in the mini superspace, and in principle as well to any desired order in classical expansion. We only need to choose an appropriate parameterization for S because everything is parameterized by that S. And we propose this parameterization in a way in which we can incorporate the same situation as in the Euclidean approach, that is that we have a bubble of true vacuum inside a background of false vacuum. So in this way, we're going to propose the S parameter in such a way that from 0 to some value S bar minus delta S, the scalar field has the value of the true vacuum from S bar to plus delta S to Sm. It has the value of the false minimum, and we are going to have a wall of width 2 delta S where the scalar field changes its value, and we're going to consider always the thin wall limit in which delta S is 0. So with this parameterization of this parameter, we're going to be able to obtain the same results as the Euclidean approach in the simplest cases, where we are also going to be able to consider more important and more interesting scenarios. So now this is the end of the general method. Let us start with the simplest case, which is let us consider general relativity with the FLRW metric with positive curvature. So this metric describes a universe which is homogeneous and isotropic. And it is written in this way. The only degree of freedom coming from the metric is the scale factor, which is in the special section is like a sphere with a time varying radius. So the Hamiltonian constraint takes this form. So as I said, the generic form works because we only have quadratic terms in the momenta, and then the term that we were going to call F. So we don't have linear terms in the momenta, and in this case, since the special slice is compact, the volume of the special slice is just going to be 2 pi squared. So we proceed. In this case, the starting point in the scale factor, we are going to take it as 0, so we can investigate, and this is going to be the goal to investigate the very early units. In this way, the gamma function, which is going to be the logarithm of the transition probability, takes this form. It will always take this form, which is 3 integrals. The first integral is in the region where the scalar field takes the value of the false minimum. Second integral is the region where the scalar field takes the value of the false minimum. And then we have an integral of the wall, and we're going to use the thin wall limit. So these 2 integrals are going to be solved by solving the system of equations and turning from integration of S to integration of the scale factor, and then we compute it. But the third integral is not going to be computed because of the thin wall limit. What we're going to do is that we know from the Euclidean approach that this integral is actually a tension term where it's written like the volume of the special slice, then the function that is coming from the degree of freedom evaluated at the wall, and then a tension term, which is going to be a constant. So in the Euclidean approach, we have this relation, so we also use it here. And by doing this, we obtain, for the simplest case, the closed FLRW metric, the semi-classical result, this expression. So here appears the sign ambiguity on the left-hand side is the one that we have encountered earlier, but the sign ambiguity on the right-hand side is not related to this one. This comes from the fact that the system of equations gives a solution for C squared, but we need C. So we have 2 sign ambiguities which are not related, but we're going to choose the correct sign in order for this to have the correct behavior of probability. Now, this transition probability is described by two parameters, A bar and P. A bar is the scale factor coming from the metric, and we're going to interpret this as distribution probabilities of creating universe at a given size, at the size of A bar. P will be dependent parameter, which is going to be attention term. Now, in the Euclidean approach, it is proposed that these two parameters could be related by extremizing this expression with respect to A bar. This can be done in here, but we obtain an expression that will not be valid for every values of A bar if the potential minima are positive. So here in this example, this is the only limitation, but in examples that we're going to be further on, there are going to be more and more difficulties. So we are going to always take those parameters as independent because general behavior dimension. Now the results, these results here coincide with the one that was obtained by using the Euclidean approach, the A2 by part, and the approach of the Lorentzian method by Quevedo and collaborators, where they use these same ideas, but they use a particular value of C, like they propose by hand, and here we do not propose it in a particular manner. Instead, we solve the system of equations, and we have a particular form of this, where the results comes out. Now, one important point that we can see from the results is that when we take the limit of A bar goes to 0 of this expression, we obtain 0. So yeah, and since this is the logarithm of the transition probability, the probability will go to 1 as A bar goes to 0. So the maximum probability will be at the initial singularity. Thus, we understand this result as stating that the most probable scenario to have this creation of a universe so vacuum decay is that it starts with an initial singularity. At least here.
Daniel, sorry, a silly question. Actually, can you repeat again what was t? Because in that limit, t goes to infinity. So what that it means?
D, which D?
And the limit a the scale factor going to 0 in the equation 33 and the previous slide. That equation, if you take the limit, t goes. So now I forget what was the meaningful of t, because what it doesn't mean that goes to infinity. Or you say it was independent. I got lost a bit there. Just explain that.
Yeah, well, that's precisely one of the problems. Here, if we take it goes to 0, it's eliminated. There's no dependent VA. But what I said is this tension term, this attention term, it can be related can be related to A bar, but it is in a restricted way only. So we say that they are independent. So in this expression, what you need to understand is T is independent of A bar. And if we take A bar goes to 0 to all this whole expression independently of T, it goes to 0.
Okay, and also there is a with order free. Scale factor has order free in front, so in any case that wasn't a problem in the limit of the scale factor going to 0 as well. I guess. Okay, but I understand what you say. And okay, A was the real vacuum, and B, sorry.
Yeah, see.
In the notation,
A is the true vacuum, B is the false vacuum.
Okay. Okay, thank you.
Okay. Yeah, so that's the result, and this coincides with the Euclidean and the Lorentzian. But as I have said, we are not limited to this very simple method. We can go beyond and more interesting method. So we're going to consider now a Yankee method, which describes a homogeneous but now an isotropic unit. We're going to see what is the what does anisotropy change for the transition probability. This metric at this form is like having 3 scale factors, one for each direction, and we only have one this term, which depends on alpha, which is a constant that is measuring how big is the anisotropy. So in this metric, it's isotropy limit, it's equal to 0, and all the scale factors are equal. And you will lead to not to the closed FLRW metric, but to the flat FLR. Now the Hamiltonian constraint for this Bianchi-Tree metric has this form, so it's more complicated, but we can identify the general form that we have seen in the method. Now the metric superspace is not diagonal, it's more complicated, but we can work it out. The function is this. We do not have a linear tension in the momentum, and now the volume of the special slice is not is divergent if we consider all. If we do not compactify the special slice, but the compactification is working. So we are only going to follow the general overall constant of relativity. Now, as we saw in the general method, for the regions of constant scalar field, the degrees of freedom coming from the metric gets related. In this case, they get related in this way. So for positive potential minima, it is more convenient to work with the A variable. For negative potential minima, it is more convenient to work with the two expressions will be the same. Now everything will work out as in the other case. We will also have definition of attention term with this integral, and the result in the classical approximation we have this one written in terms of A. So we have as well two degrees of freedom, two parameters, one coming from the method, which is A bar, and one tension tense that we will consider as independent variable. In this case, by taking a specific choice of the tension, by plotting against A bar, plotting this expression now, the flat FLRW result is the same as the flat and the closed FLRW result that we saw. So the probability starts at 1 and goes to 0. We know that all the Bianchi results have the same general form. They all start at 1 and go to 0. So the most probable scenario is again initial singularity. But now as the anisotropy is increased, the probability is decreased when considering positive potential. And as well, if we consider a particular value of A bar and we vary with respect to T, we also have this behavior. But if we consider negative potential minima, it means functions a little bit. We have two regions, two different behaviors. In the first region, we have that as anisotropy is increased, the probability increases. And then for bigger scale factors, we have the same behavior. But what is important here is that anisotropy changes a little bit the transition probabilities, increases it or decreases it, but the general behavior that they all start at 1 and goes to 0 as we increase the scale factor remains. So in general relativity, for isotropic or anisotropic metrics, we always have at the semi-classical result, at the semi-classical level, that the most probable scenario is to have a special singularity of the universe. Okay, so it was this result was general relativity. Now let's move on to another theory of gravitation, which is the Fayet-Lynch's gravity. Because as you have already said, the general method only relies on having a generic form of the Hamiltonian constraint. We do not require specifically general relativity, so we can go to other theories of gravitation, so as long as the Hamiltonian constraint has this general form. So we're going to consider Fayet-Lynch's gravity. So in case you are not familiar with it, it is a proposal that employs an anisotropic scaling of space and time variables in such a way that in the ultraviolet it breaks Lorentz symmetry, but as a result it renders the theory normalized. So in this way, it is a theory that has a better description in the ultraviolet than in relativity. The gravitational action for this theory has this complicated form. The important point here is that we have a lambda parameter, which tells us the information about the specific foliation of the space-time. Lambda goes to 1 and corresponds to the same foliation as general relativity. And then we have a lot of new extra terms, or with the constant gi. And all these new terms are higher order derivatives, but only on special coordinates. The time derivatives are only of order 2. So in this formalism, the metric has the same ABN form, so we can compute the same analysis as before. We can do the negative equation and so on. And as I said, since variability-graph has a better behavior on the ultraviolet, they are a better scenario to study transition probabilities because we expect to have a better description on the ultraviolet. So we're going to use the more general version. The more general version is to consider all these terms. In particular, an scalar field is coupled into this theory in a different form than general relativity. We have, in the first term is similar to general relativity, but in this case we have new extra terms. Here is there's going to appear the potential scalar field as always, but now we have special derivatives of the scalar field. So if the scalar field is a homogeneous scalar field that only depends on the time variable, then this action is going to be very similar to the general relativity case. But if the scalar field can depend on special variables, this action is going to be more difficult. So we're going to consider both cases in order to try to get as much information from the Koyaba-Lich's gravity as possible. Now, in this case, we have two new terms, C1, C2, and C3. C1 is going to correspond to the velocity of light in the infrared, so it's never going to disappear. But C2 and C3 depends on the scale of energy, so we can neglect it in some limit. So in the infrared limit, where lambda goes to 1 and all the Gn goes to 0, an extra degree of freedom is going to survive coming from this one, C1. So in the infrared limit, we're not going to get general relativity, we're going to get general relativity plus something more. But it's going to look very similar to general relativity. Okay. So now there was basic concepts of Koyaba-Lich's gravity. Now we are going to compute the transitions in this theory of gravitation. So let's start with inhomogeneous scalar field that depends on the time parameter, but also on the special variables. So in the general method, we supposed that the fields on superspace were homogeneous. So in order to be able to apply the general method, we are going to use expansion in spherical harmonics in S3 of the scalar field and the potentials, so we can focus on these scalar fields and these potentials that are homogeneous. So we are going to obtain a mini superspace which have a lot of more a greater number of fields, but all of them are going to be homogeneous. So the Hamiltonian constraint is this form. It is far more complicated, but it has the same form as before. That is, you have square terms of the momenta, and all this is just a function f that does not depend on the momentum. So we can just identify it, and we work with the general method as before. Here there appears some constants, which are just integration of the spherical harmonics chemistry. And again, we do not have linear terms in the momentum. We only have quadratic terms. So we proceed as always. In this case, the parameterization of S, which was in the whole scalar field, corresponds to this parameterization in all the homogeneous scalar fields, which is the same form. And the same happens for the potentials. So in this way, the logarithm of the transition probability takes this form, which is more complicated, but it has the same form. That is two integrals that can be solved by going to integration of the scale factor, and then we have more integrals that are going to appear in the thin region of the world. So all these integrals are going to be interpreted in the same way as before. That is, we're going to define new effective potentials, and for each effective potential, we define a tension term, or with their corresponding dependence on the scale factor. And by doing this, we obtain for an homogeneous scalar field the same classical results. Now, it looks very, very interesting, but the important point is that it has 5 degrees of freedom, 5 parameters, 1 degree of freedom coming from the metric, which is, again, the scale factor evaluated at the wall. And now we have 4 tension terms. And all of them are going to be independent parameters. And in particular, all the tension terms must be chosen as positive constants. Now, from this result, we can study the limits. In the infrared limit, we obtain a result that looks similar to GR, but with one extra degree of freedom, as we have anticipated. And in the ultraviolet, we get this result. But we note from here that if we go the limit a bar goes to 0, this is not going to go to 0. So in the ultraviolet, we get something that is going to change dramatically from the GR result. So when we plug numbers on it, we have this plot. So the general relativity result is the blue one. And as we have seen earlier, they all start, the general relativity result starts at 1 and goes to 0. Koyavalich's gravity for big values of the scale factor on the infrared, we have the same form of general relativity, that is, it goes to 0, and it only changes for the different values of lambda that we can take. But in the ultraviolet, instead of going to 1, it goes to 0. So in Koyavalich's gravity at the semi-classical level, we obtain the result that the universe should not start at its initial singularity. It should be created at a small size of the scale factor, but different from 0. So we are having a plausible resolution of the initial singularity by considering this transition in Koyavalich's gravity. Now, this was for
Daniel, sorry.
No, I also have a question.
Just in my case, just a small question. The beginning of this probability transition that looks like 0, does it change with the distance between the two vacuums, A and B, or this means that the ultraviolet they are so far away, or that the energy the field cannot happen a phase transition. Yes.
Yeah, no,
I know
the different values of the scalar field minima will have an importance here. How high is this? How to the left or how to the right? But that it goes to 0 in the ultraviolet, that does not depend on the value of this, because it only depends on these tension terms.
Okay.
They are independent ones.
Okay. So sorry, Dimitri.
There was another question?
Oh, no problem. My question is simple. You see, as you said, there is a size value of the scale factor for which the probability has a maximum. I just wanted to know if you derived an analytical expression for this scale factor of maximum probability, or if it is just numerical. Have you obtained it as a function of the other parameters?
Yeah, no, we have not obtained it because this point, the maximum probability depends on the specific form of how inhomogeneous the scalar field is, because it depends on the specific specific
I see.
expansion. Yeah.
Okay. I see. But in principle, if one chooses a specific potential, a not very complicated one could try to do this calculation and obtain the form of the maximum probability scale factor for each potential, right?
Yeah, it can be done.
Okay, thank you.
You're welcome. Okay, so this was Koyavalich's gravity with an inhomogeneous scalar field. We now move on to a simpler case, but, which is a homogeneous scalar field. So in here we do not need to do all the expansions. We only look at the scalar field, and we follow the method as before. And what we obtain here is a result that only depends on 2 parameters, as in general relativity, A bar and T. In the GR, in the infrared and ultraviolet limits, we obtain the same behavior as GR. So this is not a very interesting case, because in the ultraviolet here, it does not, it also leads to the initial singularity, right? So in order to have this avoidance of the initial singularity, the scalar field must be homogeneous. We have an homogeneous scalar field, we obtain a very similar result as in general, at least at the semi-classical. So now, up to this point, we have not used the full general method because there are always appears Hamiltonian constraints that do not contain a linear term in the moment. So let us investigate a form in which these linear terms will appear and that will be interesting. And it is called a generalized uncertainty principle. So first, a few basic concepts of this. So it is believed that any quantum theory of gravity should contain a minimum measurable length. This phenomenological fact can be incorporated to standard quantum mechanics by modifying the Heisenberg. So instead of having just I, we now incorporate this term in square momentum, where this gamma will be related to the minimum measurable length, so it will be a small parameter. So if we change the Heisenberg algebra in this way, we will obtain a different uncertainty principle, which is called a generalized uncertainty principle, that is a COP. Now, this procedure can also be performed in the mini superspace, and in this regard, it is expected that the Wheeler-DeWitt equation will be modified, in particular, linear terms in the momenta will appear, and it is expected that by doing this, we improve the ability of the Wheeler-DeWitt equation to describe quantum gravity phenomenology. So it is a modification by hand that we are trying to incorporate a phenomenological act of quantum gravity. So by doing this,
regarding equation 7.7, I cannot see how this specific modification by adding this extra term implements that there is a minimum length. I can see it. Is there an easy way to see it from this equation?
Yeah. Well, the general uncertainty principle, if you recall, are uncertainty in X, uncertainty in P, and it is bounded from below for this specific commutation. So in the standard way, it's just I, and then it goes H bar over. But by doing this, it gets a minimum measurable value for delta X. This is not the only possible modification, but it's the simplest one.
I see. But so one should use this commutation relation, apply it to derive the relation between delta X and delta P, and one will see that delta X will be bounded from below. Is that the idea?
Yeah.
Okay, so now I got it. Thank you. And one more question. That gamma, that small gamma, is that the Barbero-Imse constant from loop quantum?
No. In this case, it's
the same notation, right?
Yeah.
Okay. There you go.
Okay. So we're going to use this in the context of the Wheeler-DeWitt equation, and we're going to compute the transition probabilities by considering these terms on the Wheeler-DeWitt equation. So we're going to consider a generalization of this scope to apply to all the variables in the superspace. In particular, I'm only going to show results for a closed LRW metric, which is the simplest metric, and the scale factor will be written as an exponential. In this way, the Hamiltonian constraint looks like this. It is far more complicated. It changes all the terms, but in particular, it adds these linear terms in the momenta, as we expect. So we now use the full potential of the method. But we are going to use approximations for this GO parameter to be small. And if we do so, we can compute the transition probabilities after we identify all this, and we obtain this result. And now it's far more complicated, but we only have as well two parameters, one coming from the metric, which is a bar, and one independent parameter, which is the tension. Now, even though they look very, very different in the ER result, since gamma is very small, when we plot it, they actually look very similar. So what changes is for small values of the general form does not change. It has the same general form, that is that it starts at 1 and it goes to 0 as in general relativity. But for a small values of the scale factor, the probability is increased as the GOP parameter is increased. And then we have a change of behavior. When the scale factor is big enough, the behavior is flipped. and the probability is decreased as the Go parameter is increased. But the important point here, hoop is Heisenberg's principle that is without the Go. The important point here is that for small values of the scale factor, the probability of creating a universe with a non-zero size is increased with the Go parameter. So we have a consistent idea that the phenomenology of the Go is incorporated in these transition probabilities. Now, this can also be done for more general metrics.
Daniel, sorry, a little question. If I understand correctly, that gamma equals 0 shouldn't coincide with the previous result without the modification in the Heisenberg principle.
Yeah,
okay, if that's then so. Okay.
Yeah, I just plotted with a small range so we can see it. But if I plot the whole range, we will have the same one.
But you say also that you were taking a gamma much smaller than 1, and there you put 0.5 and 0.7. Sorry for the silly question, but that's not very small comparing with 1.
Yeah, this was only done so we can see it clearly what is the behavior.
Okay. But you neglect something when you take that limit before, right? So okay, you are using it because you're saying that you have better plots. I understand, but don't you have to consider extra term or something like that if you're not going to take gamma small, basically?
No, I think this work fine.
Okay, thank you.
Okay. So this process can be performed with more interesting metrics. In particular, we can do it with the Bianchi metric. I'm not going to show you the results because it's very, very messy, but the important point is that with this metric, we obtain consistent result. That is, when we vary the anisotropy parameter, we obtain the same as general relativity. And when we vary the Go parameter, we obtain the same as with the FLRW metric. So it is consistent to study the GOP and the anisotropy at the same time. Now, all of these results that I have just shown are at the semi-classical level, that is only considered in the first order in the semi-classical expansion. The newest result that I have today is considering transitions now with quantum corrections. And we're going to go to the basic, that is, we're going to consider general relativity and the simplest metric, the FLRW metric, although we have also considered more interesting metrics. So the computation of quantum corrections in the Euclidean approach that is considering loops, a contribution to this Euclidean approach has been very troublesome. It has not been done on all these decades because it is not well defined and it's contradictory results. So in the Lorentzian approach, we can consider quantum correction by considering higher order terms in the WKB expansion. For field theory, when there is no gravity, these terms, considering higher order terms in the WKB expansion, are equivalent to considering loop contribution to the Euclidean pathicity when there is no gravity. But when there is gravity, it is not entirely sure if there is this exact equivalence. So we're going to do it in the Lorentzian approach where we can do it because the Euclidean approach cannot be done, or at least until today it has not been done. And these contributions of considering higher order terms in the WKB expansion will be quantum gravity corrections to the transition probabilities. So as I presented earlier, when considering quantum correction, the transition probability will have the same form, an exponential of gamma, and this gamma will have three contributions, gamma 0, gamma 1, and gamma 2. Gamma 0 will be the same as before, as all the semi-classical results we have shown. And now gamma 1 will have S1, and gamma 2 will have S2, and we have to compute S1 and S2 as well. And as I said, we were going to consider a closed FLRW metric only, which is the simplest metric, and general relativity. So in the semi-classical result is the same as before. The important point here is that it has dependence on two parameters, A bar and the tension term, which we now call T0. Now, the first quantum correction has this form. Now, it adds only one extra term, which is a tension term T1. And the important point here, well, important points. One is that it depends on higher derivatives of the scalar field potential evaluated at the minimum. So in the semi-classical result, we only have the potential evaluated at the minimum. Here in the first quantum correlation, we have the second derivative evaluated at the minimum. And this form in particular, this to an upper bound for the scale factor if we consider positive potential. So we have a result that is that restricts the validity for the scale factor. Now the second quantum, this in particular does not change the general form. As we will want to see in a minute, it only changes a little bit the probability. But the second quantum corrections will be more interesting. Now it adds one extra new term, which is a potential term as well, and it depends now in higher derivative of the potential minima, now fourth and third derivatives. And we have a new extra restriction of these higher derivative terms in order to have a well-defined probability. So if all of this is met, we obtain this form. Now the semi-classical contribution, as we have been seeing all this time, they all start at 1 and goes to 0. The first quantum correction does not change the overall behavior. It has the maximum probability at the beginning as well. But the second quantum correction in the infrared can be neglected, but in the ultraviolet, it modifies entirely the behavior, leading to the same form as the one we encountered with avalanche gravity, but now in general relativity, considering second quantum correction. So in general relativity, with a homogeneous and isotropic universe, considering second quantum correction to the transition probabilities, we are led once again to an avoidance of the initial singularity. We can also perform this analysis for anisotropic metrics, in particular for the Bianchi metric. But what we encounter there is that the avoidance of the initial singularity is only possible for the isotropic universe. For the Bianchi metric, the singularity still remains at the maximum point of probability. So this appears to be only possible for the isotropic universe. Okay.
So
yeah.
You have been discussing the Bianchi metric case, but I suppose it was some algebraic simplifications or something like that. But have people performed these calculations for other Bianchi types? I don't know, for Bianchi 1, which is the simplest, Bianchi 9, which has closed special section. Can the singularity be avoided in other Bianchis, or these calculations have not been done yet?
Yeah, well, we use the Bianchi metric because it has the most the simplest isotropic limit. I mean, it's only this isotropic parameter, and when we go to 0, we obtain the isotropic result. Other Bianchi metrics can be put in these computations, but the isotropic limit is more difficult to be seen. So I'm not entirely sure if using another metric can be alleviated. Okay.
Actually, no, because I was speaking English and someone came here thinking that I'm not from Brazil. I didn't got your last explanation. Could you please repeat it?
Okay, yeah, that we use.
I'm really sorry.
Yeah, don't worry. We use Bianchi metric because the isotropic limit of Bianchi metric is very simple. It leads to the flat FLRW result just by varying the value of the alpha parameter, or the anisotropic parameter. Another forms of the Bianchi metric, it is a little bit more difficult to see what is the isotropic limit regarding to an FLRW metric. So that's why we only have used a Bianchi metric, but the method is general enough to consider another metrics, and I'm not sure if by considering another Bianchi metrics. We have also used Kantowski-Sachs metric, and we obtain the same problem, that the initial singularity is not avoided. Also in Kantowski-Sachs metric, which is another anisotropic metric, which are not related to the Bianchi metric.
Actually, I found it interesting that you said that the Bianchi tree is simplest in the stage, because I have worked with Bianchi 1, and I think one can define an appropriate isotropic limits. Why would there be, why would it be more difficult in that case, for instance?
Yeah, what happens with the Bianchi one is that we need this alpha parameter in the Bianchi tree, because if we do not have the alpha parameter, we consider, for example, Bianchi one, the form. Okay, let me go. Okay, give me a minute. Yeah, these relations, if we do not have the alpha parameter, then it relates like the 3 scale factors are equal. In order to compute the transition probability, the 3 scale factors are equal. So we lose all the information of anisotropy. We need this alpha parameter. So if we try to use the Bianchi 1 metric, that is what happens. We lose the information of anisotropy. So it is in this regard, is like Bianchi 1 is too simple.
Okay. So okay, I see. And in the other cases, one would in principle perform the calculation, but it would be hard to compare it with the isotropic limits. Is this correct? Did I get it?
Yes. Yeah.
Okay. Thank you.
You're welcome. Okay, so to end today, let us talk about some final remarks. So the study of vacuum transitions is highly relevant for canonical quantum gravity, because it is the only, well, as far as I know, the only formal statement to describe the birth of a universe. So we presented a general method, which is in principle valid for any model in the mini superspace and up to any desired order in semi-classical expansion, that is up to any desired order in the quantum corrections. In general relativity, we have obtained compatibility with previous results, both in the Euclidean and the Lorentzian approach. But we can also study the effect of anisotropy. We can study transition in another theories of gravity, such as Hoya-Valenci gravity, where we obtain, even at the semi-classical level, a plausible resolution of the initial singularity. We can consider modifications to the Wheeler-DeWitt equation, such as incorporating a GOP, and in this way we improve the probability of creating universes with a non-zero size. And finally, we can compute also quantum gravity corrections, in where we obtain a resolution of the initial singularity, at least for the isotropic universe in general relativity. And to end, I will give you some references if you are interested to see a little bit more. Here there are the 4 papers I talked about today. Transitions in general relativity is this one, transition in Hoya-Valenci gravity, transitions with a group, and the newest results are a couple of months ago, the transitions with quantum corrections. So that will be all. Thank you very much for your attention.
Great. Thank you, Daniel. Really interesting. Let me stop the recording and we can start with a lot of questions.